Hello everybody. Today we're going to be going through recitation activity for week 9, and in this case the problem is going to be using concepts of conservation of energy and energy transfer via mechanical work. And so we'll go ahead and get started. So the problem has this figure below, which has some block on a spring, some spring constant, and it's being held in place, which is compressing the spring by a certain force, constant force of 120 newtons. Once the force is removed, the spring will, through the restoring force, cause the block to start moving. And as the spring decompresses, the decompression, the potential energy of the spring, gets, you can say, transferred to the kinetic energy of the block, and so the block departs the spring at some final distance with some initial velocity. The block's momentum then carries it up the hill and to the other spring. So what we see is multiple energy transfers throughout the system. The block initially starts with some initial energy, and then as the spring decompresses, it has some potentially new energy with some initial velocity, and then it continues to move up with that velocity, and there's no friction on the surface, so that velocity will stay constant. And then right before it hits the friction zone, it's going to have some new velocity and some new energy, potentially new energy. And then as it hits the friction zone, what we'll see is friction acting on the block, and therefore transferring energy or doing work to the block to remove kinetic energy from the block before it hits the spring. And then it hits the spring, and whatever energy it has after will be transferred to some potential energy compressed in the K2 spring. So the question you ask yourself before starting these problems is, at what points in its motion up this hill and through the friction zone into the spring is the energy changing? So initially what we see is potential energy given to the block through the work done against the spring. Because in order for the block to be compressed against the spring, a force has to be applied against the spring of a certain amount across a distance that is compressed in order to compress the spring. So that means work is done against the spring, because work is a force times the distance or displacement. And so in this case, the initial energy is just going to be the energy associated with the potential energy of the spring, which is 1/2 k delta x. And it's no coincidence that this formula looks similar to kinetic energy, because the way this potential energy of the spring is derived, what we call mu s, potential energy of the spring, is using the definition of mechanical work. So if we give this the direction xhat, then the force F, which is working to compress the block against the spring, would be equal and opposite in magnitude, or equal and opposite of the spring force. And the spring force is negative kx. So what you get is positive kx, in that negative xhat direction, dotted with dx, from 0 to some final change in its displacement delta x. What we do is then integrate over this distance, and we get 1/2 k x squared, and plug in delta x and 0. So then what we do is integrate this from 0 to delta kx, and you get 1/2 kx squared, and then you evaluate that to bounds. That's 1/2 k delta x squared. Now, this will always be kind of true when you compress against a spring. So then that's why we call this, give it a name, and it's the potential energy due to the spring. And it's really just the reason there's energy associated with the spring in the first place is because you're adding energy, you're transferring energy through the work you're doing to compress the spring and giving it to the spring. And this is the form it takes. So without doing this integral, we can know that when a spring is compressed by some distance from its equilibrium point, or its natural length, I should say, that the energy associated with that is 1/2 k delta x squared. So that's the initial energy associated, or the energy associated with this system when it's compressed. And now what we're going to see is when that force is let go, this energy is going to transfer into a different type of energy, and in this case it'd be kinetic energy because it's going to be impart a velocity to the object, and that's E2. So E2 is just going to be equal to 1/2 mv squared, and we'll say that's V initial. And so then through energy conservation we can equate EI with E2. So then we have 1/2 k delta x squared is 1/2 mv initial squared. We're given V initial. We know we don't necessarily know k, but we need delta x. So then in order to solve this equation through energy conservation, we need to plug in something for k to solve, because right now we have two unknowns in one equation. Well, we are given a magnitude of the spring force, and that's equal to, in this case, just k delta x. And this is 120 newtons. So then what we can do is solve for k in terms of delta x and the magnitude of the force, and plug this in to this equation. So then what we get is 1/2. We can cancel the 1/2 from both sides of the equation and plug in k as 120 over delta x, and what we end up getting is 120 newtons times delta x equals mv initial squared. And so then delta x, the distance it's compressed, is equal to mv initial squared over 120 newtons. And just to make sure that the units make sense, and delta x is a change in the x dimensions, so it should be in meters units. So this right hand side should be meters. Well, this is kilograms times meters per second squared, so meters squared over second squared over newtons, and newtons is kilograms times meters per second squared. So then what we get is seconds cancel, 1 meter cancels, and kilogram cancels, and so we're left with meters. So this answer unit wise makes sense. It's a good check always. So then we know the energy before it goes up the hill. Then what we want to ask is we want to get the energy change, if there is any, from the point it leaves the spring with energy E2 to the point where right before it hits the friction zone. Well, in this case we have no friction, so we don't have any non-conservative forces. If we have no non-conservative forces, then every force which is acting on an object in order to change its kinetic energy is conservative. Thus, the energy from E2 to E3 is conserved. You may have to rewind that if that was a little confusing, or word gymnastics maybe, but in this case then we can equate the energy that the block has after it leaves the spring, E2, and equate that to E3, which is the total energy it has once it's up the hill. Well, we already know the energy, what form it has in the case of E2, and E3 it still has some kinetic energy, and then it has an increase in its height, so it has some increase in potential energy. Well, if these are equal and h is non-zero, then this must be a different velocity, right? If these sides equal. So then we can solve for that velocity. And so what we get is this final velocity at E3, at the point before it hits the friction, is equal to, by doing algebra, we can subtract over to mgh and multiply both sides by 2 and cancel the m's. So we get v equals, and then square root both sides. So we get v equals v naught squared minus gh 2gh. So this will be our final velocity. And now we can plug in our initial velocity, which is given in the problem. G is a constant acceleration, and h is the height difference, which is given in the problem as 0.2 meters. And that's our final velocity right before it hits the friction zone. Now, of course, when we square root both sides, mathematically we get a plus or minus square root answer, but we picked the positive root because physically what's happening here is a velocity decrease from here to here due to energy conservation and a height change. So for these two energies to be equal, with the right hand side having two terms, this final velocity has to decrease. But we know it's not going to be negative. So we're going to take the positive root as our answer. So now we have the velocity before it hits the friction zone. And now what we're given is that this block actually hits the rough patch and encounters a spring at some distance through the friction zone, and then compresses the spring a certain amount and then stops. So what this means is what we have here is friction, and friction is a non-conservative force, so that means it's going to actually remove or change the total energy through time of our block, which means that it's doing work, which is energy transfer, going to do work against the block to transfer energy from the block to make its final energy, let's say at E4 where it comes to rest, to be less than E3. Well, we know what E3 is. It's some kinetic energy with some final velocity and some height, right? And then we know E4 is less than E3. And specifically, since we know exactly what forces are acting on the block in a simplified picture, right? We have gravity, normal, and friction. Normal and force of gravity are normal to the path in which it's moving, so automatically we know it's not doing any work to the block. Thus, the only thing that's doing work is the force of friction, which is removing that energy from our system since it's a non-conservative force. Well, we can account for this because we know the total distance that the block travels from E3 to E4 is d plus some unknown amount, which is x, we'll call x, which is the amount that this spring gets compressed. Say that's amount x. And that's what we're going to want to find. Well, since the force of friction is proportional to, or in this case, the magnitude of it is equal to the normal force, and this block is on a flat surface, then we know that this is a constant force. So we can, if for a constant force, we know the work done is equal to the magnitude of the force. Let me move this. The magnitude of the force, which would be mu k, magnitude of normal force, times the distance of travel, times the cosine of the angle between them, between the path and the force of friction? Well, the path is this way, right? It's moving to the right, but the force of friction is to the left. So the angle between those two things is 180. And cosine of 180 is -1. And so we know that the work done is equal to negative mu k, magnitude of normal force, times the distance to travel, which is our distance d plus some compression amount x. And so we can rewrite that in terms of mu, because we know the magnitude of the normal force on a flat surface is just mg, m magnitude of g. So mg and then times d plus x and negative. So our work has a negative sign. Does this make sense? Let's think about this for a second. Work is quantifies the energy transfer of a system. Well, what's happening in this picture? Friction is working on the block to remove energy from it. So that means the work it does should be negative. The negative sign will indicate that the energy transfer is out of the block and into the space outside of it. Through, in the case of friction is usually either through sound and heat, right? When something slides across something, what do you get? The surface heats up a little bit, and also sometimes it makes a sound, vibration. And so that's what's happening, right? So what's happening is the friction is transferring the kinetic energy of the block into heat and acoustic energy. And we can quantify that exact amount due to definition of mechanical work, since we know how to write the friction force in terms of things we know. So then, what can we say? Well, E3 is greater than E4 because energy is being lost. But we could say, since we know exactly what's causing the energy loss, and we can calculate the work done, or that energy transfer, that we can actually equate it to E4 with the stipulation that we add the energy lost due to friction. And so, then all we have to do is write out E3 and E4. E3 we know. We need to go and find out what E4 is. Well, E4, it doesn't have kinetic energy at that point because the block comes to a rest. The change in potential gravitational energy from E3 to E4 is 0 since it's on a flat surface. And the only other energy it could possibly have is the potential energy due to the spring being compressed by a certain amount. And so we can say, so then E4 is really just that, which in this case would be K2 delta X. And so on the left-hand side, we know this. We can calculate this. And let's see what else we're given. We're given a spring constant. And yeah. And so we're given a spring constant. And so what we can do is write out the work due to friction, which we already worked out that expression. It's mu k mg magnitude d plus x, and it's negative, plus 1/2 k2 delta x, and that's going to be equal to the kinetic energy the block has before it hits the friction. And so then we can, in this case, we can solve for x. So what we have here, we can distribute our terms. Distribute our terms, mg, I'm just going to call magnitude a g vector just g for simplicity, plus mu k mg x plus 1/2 k2 x squared. Sorry, forgot my square up there. 1/2 pf. We need to solve for x. So what we have here is a quadratic equation. So then what we want to do is to solve a quadratic equation, which we know how to do. So what we'll do is multiply everything by 2 and divide by k2. So we get x squared, and move everything to one side so it's equal to 0. And so what we get is, let's see, x squared plus mu k, 2 mu k mg over k2 x minus 2 mu k mg d divided by k2 plus m over k2 vf squared. So this will be our constant term in our quadratic. This will be our b term, and I guess this 1 times would be a. So then what we have to do is use our we can solve for our roots. It's negative b plus or minus square root of b squared minus 4ac over 2a. Quick caveat, as you notice that when we solve for this using the quadratic equation, we actually get 2 roots, and we know that there's only one distance from equilibrium that this spring goes, but we get 2 answers. And how do we decide which one to pick? Well, what it comes down, at least in my eyes, and the way I think about it, is that what we're trying to get is a distance that the spring goes from equilibrium in order for the energy before it hits the friction zone to be equal to the energy after it hits the friction zone, goes through some compression, and stops, and while accounting for the work done by friction, and we equate them. Well, the 2 roots really, in my eyes, represent the 2 ways in which a spring can go. It can either stretch or compress. And so if you calculate the other root using negative square root, then you end up getting a negative answer. And if you go back in the video, you see that the direction in which we picked to be positive is to the right. And so a negative distance would mean that the stretch isn't being compressed, but rather is stretching, which physically doesn't make sense to happen. So you pick the positive root, and that's how you get positive 0.245, which represents a compression distance, a distance it goes after it hits a spring and compresses by a positive amount. A negative number would represent stretching. Caveat over. Okay, so then there's one more problem here, and that's this, part 2, which says there's a conservative force that has a potential energy, which all quantities are in base standard units. Determine an expression for the force. So this is pretty, I guess, straightforward as long as you know it. And that's any conservative force, keyword conservative force. Any conservative force can be described by a potential energy function. And so if you're given a potential energy function, then the force is equal to the negative gradient of that potential energy function. And so, this comes about through vector identities in calculus, and a good explanation can be found, and proofs can be found, and even though you haven't been taught the topic yet, and you will next semester, in Griffith's Intro to Electrodynamics, Chapter 1, it talks about this identity and goes through all the equivalent statements that can be made about a force which is given as a gradient of a potential. So that may be worth checking out for you, even though that topic in electrodynamics you're not doing yet, and that book itself may be a little higher level than your Physics 2 class. It has very good proofs and explanations of this. So then all you have to do to find the force is take the gradient, negative gradient of that potential. And so the gradient is a vectorial type quantity. It's defined as the partial derivative with respect to x in the x hat direction plus the partial with respect to y in the y hat direction plus the partial in the z. Or well, in the case of 2 dimensions, it would just be this. And this may be a little confusing because vectors have direction and a number associated with the direction, but a gradient, this is a partial derivative. It's an operator, it's not a number. So it's kind of a weirdly defined thing. And we use this just all the time because in physics it's just used all the time. And so that's why this has some special name. And so the gradient is a vector like an operator. It operates on vectors and is technically like a vector itself. But it's not something that has a size and direction. It operates on a vector to give the size and direction of the slope of the potential, which would be the force. So, which you can kind of see through this definition, right? It tells you how much the potential is changing with respect to x in the x direction, plus how much the function changes with respect to its second parameter y in the y direction. So then we can take the gradient of our function u, and so what you get is d dx of 11x squared minus 14xy minus 2y cubed x hat plus d dy of 11x squared minus 14xy minus 2y cubed y hat. And so partial derivative only acts on the argument which it has. So in this case, d dx would only take the derivative of x. And so you get 22x minus 14y minus 0 x hat plus 0 minus 14x minus 6y squared y hat. And this is our force, which has as our argument x and y. Alright, I hope that helped. Let me know in the comments if you would like to see anything more like this or any recommendations, anything at all. Alright, thank you.